walk over to the screen.
Yeah, just yes, usually it does.
Just carry the computer with you.
Yeah,
Never mind.
no, it's fine. You just have to do something. And then I'll give you this.
You know, I bought 3 of these and I've lost each of them. The last time I put a business card inside of it so that if it's
Somebody,
and it
nobody,
doesn't make any difference.
nobody brought it to you.
No, I'm reluctant to buy another one. Wow. I'm impressed. That must have been my cue also. Okay. Well, I'm Gary Reinexis. I'm a flavor chemist by training. And so I'm the one who kind of looks at the flavors of foods, the aromas, especially the smell of food. And what kind of instrument do I use to look for smell or analyze smell, take smell apart chemically? Gas chromatography. So I've been doing gas chromatography for a good number of years. So I have the opportunity to spend a little bit of time with it the next 2 lectures, this one and the next one. And so we've got a tough question for you. Might as well give you the first question. What do you think is the mobile phase in gas chromatography? Yes. Good. The stationary phase is, can be quite a number of different things, and we'll spend a little bit of time with that. What types of stationary phase? What's their role? And it's interesting. You'll find gas chromatography can be called different things. So we'll oftentimes give it abbreviations. Historically, GLC, gas liquid chromatography, used to be the name, but there's no liquid phase. The solid phase, the stationary phase, whatever, it's not a liquid. Never has been a liquid. For some reason, they said gas liquid chromatography. No idea why. I usually like the short term. It's gas chromatography. We're using gas as a mobile phase. We're doing chromatography. High resolution gas chromatography. Something that's probably happened over the last 30, 40 years. Initially, there wasn't really good separation technologies advanced. Okay, now we can do some really good separation, so they've called it high resolution. Like I said, I like to use GC. Very, very simple. What types of analyses are done by GC? Got to take your pick. You're doing fatty acids, right? Or you probably haven't come to that yet, but you'll be doing fatty acids. You'll be separating fatty acids by gas chromatography. So you can take a look at the lipids. What are the lipids made up of? What fatty acids go on in the chains? But we can also do cholesterol, gases. I want to determine whether I've gas packaged the food. Have I gotten all the oxygen out? Or is there going to be oxygen left in the package? Oxygen will spoil my food. Okay, I can measure oxygen. I can measure CO2, nitrogen, hydrogen. So really any of your gases I can measure. The solvent for purity, I can measure water in foods. Kind of overkill. There's easy ways to measure water. They don't have to have a $100,000 instrument to do that. I can do alcohols, any kind of alcohol, sugars, acids, vitamins, pesticides. You can go right on down the list. The fact that you can do them, many methods by gas chromatography, it doesn't always make sense. That's also something you think about when you read a paper or whatever. That they use gas chromatography. Should they or should they have used liquid chromatography? And that gets into some of the things like sugars. We can determine sugars. Sugars are not volatile. They won't go into gas phase. So what do? We do some magic to make that derivative that is a gas. But it's kind of overkill. Again, we should have used something else. So many, many different applications. Not always all of them make sense that you see. From a historical standpoint, chromatography kind of got going around 1850 or so. A fellow named Svet was given credit for certainly start of chromatography, separation of plant pigments. Gas chromatography has come in certainly on the late side. 1941 was the first theoretical discussion. Gosh, could we use gas as a mobile phase? Doesn't always have to be a liquid, because that's what people did then. They had a column of solid material, they run a liquid across it. But can we do a gas phase separation? 1952, the first gas chromatograph came into being. It's really awkward. So they were doing this gas phase separation, separating fatty acids, but they're collecting the fatty acids and titrating one after another after another. Really awkward. And so 2 years later, they came up with a thermal conductivity detector, which we'll mention. And basically, that made gas chromatography popular and really broadly available. So gas chromatography's been around for, 65 years? At this point, it's a mature technique. It's been a mature technique for, probably 25 years. Meaning mature, we've reached the theoretical maximum. You say, what's the best we could theoretically ever do for separation? It's there. Technology's there, the equipment's there. Liquid chromatography is still maturing. Gas chromatography, it is not going to get better. So we'll spend some time going through the technique. The sample has to be in the gas phase, and so we may have to turn it into a gas and maybe a liquid, so we have to vaporize it, turn it into a gas phase. That's oftentimes done, or generally done by heating. So you may have your sample, and your sample is in some kind of a solvent. You may put that sample into the gas chromatograph. Very hot air, it goes poof, it's in the gas phase, and away it goes. So typically, you're going to vaporize a sample. That vapor sample is being carried along by your mobile phase. Your basically carrier gas is what we call it. Passes through this column where our analytes interact with this coating on the inside of the column. And so if your analytes like that coating, and they don't want to go with the gas, they get slowed up, they get retarded. So some things go through very quickly, don't interact much. Other things interact more, they get slowed up. And so we tend to get separation based on how much that analyte, that particular compound you're interested in, likes that stationary phase. Where does it want to go? Does it want to go mobile phase? Does it want to stay with the stationary phase? Hopefully, a separation occurs if you've got a complex mixture. And then we need some way to detect it, some way to measure what we just separated. And that gets us into detectors. We'll spend some time on each of these steps and then go through how they work and how we use them. How's that? So this is a really simple gas chromatograph, a diagram of the system. We have our mobile phase over here. Mobile phase, carrier gas. Interchangeable words for us. This is going to be carrying our analyte through the system, or it's going to be the mobile phase moving through the system. So a carrier gas. We have to have some way to get a sample into this gas, otherwise the gas will just go through the column detector. We've got to have a way to get a sample into this. And so we have a sample introduction spot here. Like I say, we'll spend more detail with it. So here's where you take a syringe and inject your sample. Then it mixes with the gas here, and like I say, separation occurs on your column. We get detection here, and we generate what we call a chromatogram. This is now a little more detailed. And so here's our carrier gas over here. We've got two other cylinders. So these are the regular cylinders. So there's our carrier gas for both phase. And here we have air and hydrogen. What they do is they end up being part of our detection system. So this is our mobile phase, but this is our detection, and that gets over here as we'll see. So here we come along, so our gases are coming in. There's a nice flow control. We have to control how fast our mobile phase moves through the column. Come down here to an injection port. Here's our injection port. That's usually around 200 degrees centigrade, 250 degrees centigrade. And so there's a nice rubber septum here. I can take a syringe, go through that septum, make an injection into this hot port. Like I say, poof, it's vaporized. Then those vapors get carried into the column, and they're moving along to that mobile phase. That's a flame. That's where the hydrogen and air is. So that's our flame detector. So in this case, our compounds, uh-oh.
No, not you.
Not me?
Somebody that teaches before us here, when they leave the thing on.
Oh, then it decides to shut down.
Yeah.
Okay, do we need to respond?
No.
I thought I'd ask you.
They have their notes in front of them if you couldn't.
Okay, but I don't have their notes in front of me, so,
Right there.
okay.
Yeah.
So it will come back.
Yeah, it will. It will.
So anyway, the slide we were looking at, basically, it shows a flame. And so as our analytes come out of that column, the analytes go into the flame, and they get burned in that flame. And across that flame, we put electrical potential. So we've got a ground here at the bottom of the flame, an electrical ground, and right above that flame, we have another potential of about 300 volts. And when things are being burned, there's ions in here, we basically carry electricity across that flame. If there's no analytes being burned, we can't carry any electricity. The more analyte we burn, the greater the electrical current. So what we're doing is measuring electrical current across the flame. As long as there's something there that carries current, the more is there, the more current. So we get a response, we get a peak coming out of the system. That's the most common detector, is using a flame detector. Thinking a little bit of these gases, they do have to be high purity. So the system will easily detect nanograms getting into femtograms in terms of sensitivity. So they detect materials at very, very low concentrations. And so we have to have high purity mobile phase, or else we're going to be measuring impurities coming in, not compounds coming out. So high purity, the two most common gases are mobile phase or carrier gases, are either helium or hydrogen. Traditionally, we tend to use helium more often. For our lab, we tend to use hydrogen. Hydrogen's cleaner, it's cheap, it just works better for us. So either one of these work. I tend to like that. I've got other reasons, but more so the helium. The detector over there that I mentioned before, if it's a flame ionization, I have to have something that supports the flame. I need hydrogen to burn and air to permit it to burn. So for my flame ionization, I need air and hydrogen for our flame ionization detector. But there's other gases too for specialized detectors. And so it depends on what you're measuring. You may have no gases, no flame, or you may have some combination other than that. We have to control the speed that our mobile phase goes through that column. And so we must have good control of flow and pressure. That's determining how fast our mobile phase moves. And so we do have pressure regulators, so we can control our gas pressures very accurately. They have to be very high quality. I've seen cases where someone will say, oh, I can get a pressure regulator down at the welding shop. Not a good idea. Again, when we start talking about nanograms and femtograms sensitivity, our welding equipment doesn't meet those standards. There's diaphragms, gaskets in there. So we have to go to a special analytical supplier and get the regulators that we need. So we need a pressure regulator. Also, we need a flow regulator. How many mils per minute do we go through? They're sensitive. They're really precision equipment, and they have to be treated very, very kindly. So that's kind of the gases coming in. What gas do we need, and how do we control it? I said we have an injection port. The injection port runs, as I said, around 200, 250 degrees centigrade. And this is it. This is the working part of it. This is all set in a nice aluminum block, so it's temperature controlled very accurately. So here's our carrier gas coming in, our mobile phase coming in. Here's our rubber septum. So silica rubber septum up here, so that seals it off. So our gas is going to come in here, and some of it's going to go right across, right past this rubber septum. And most of it, though, is going to go down here, down the center of the system. So it will go down the center, and again, some will come next to here. It'll be a little more obvious why these flow patterns and what their significance is. But then here's your analytical column down here. So you make an injection, you take your syringe, you pierce this, you put it down here, we've got our gas flowing down here, you make your injection, it expands, and your analyte starts being swept down here. Some portion goes into this little column, the rest of it goes out this direction. So fairly simple system. It's interesting, probably 80% of our problems happen in that simple little system of things being clean, not being looked after. When we look at that injection port, that's one style, one type. We have different types of injection ports. That what I described as a split injection port. I showed here a pathway where we make our injection down here, and that all of our sample comes down here, but only some goes in the column. The rest of it goes out into the vent, into the room, actually. And so this is splitting our sample. You might say, wait a minute, you had just injected here, and you threw out maybe 90% of your sample. It's not uncommon, because this is a tiny column. Maybe get 2 mils per minute. I may have 30 mils per minute coming out here. So as I get this poof, only a small amount goes in here. And the reason for having it split like that is this tiny column can't manage much material. It can only handle a very small amount of material, and it's almost impossible to measure that accurately. So you put in something you can measure, and you throw it out, most of it out. So you just get a small sample of your sample of that. It's a sample of our sample that ends up going into the column here. We do have designs, and I'll show you one, where all the material injected, theoretically, all the material goes into the column. And that's what we're really looking for, really trace compounds. We can't afford to throw 90% out. I need to have everything go on that I can. So there's some compromises here that we do, but we get more material put on our column. On column, I'm going to inject my sample into 200, 250 degrees centigrade. What happens if my material's heat sensitive and it broke down? My analyte went away because of that high temperature. Well, we also have ways to do this in a cold on column system. So I'll show you again a pathway here. And we have all kinds of interesting other options in terms of injection port. This is probably 90% of the analysis in the world using gas chromatography is this method. Maybe another 5%, so we're up to 95% here. And all the rest of the applications, whatever we want, they're another 5%. So this is small. That's big, that's okay, small through here. So, if you think about it, splitless or split are really the workhorses. So this gives you a better idea of how the system works. And I'm going to, I guess, digress just a moment mentally in the sense that when we go through something like this and you say, what do I really care about all this? Can't I just inject my sample and I'll get some numbers out of it? And what do I need to understand all the stuff that goes on here? You do. You really do. The better you understand how an instrument works, the better your data, the better you interpret your data. If you treat it as a metal black box, here's a gas matter, I get my sample, I get my report and go away. You're standing a good chance of missing the boat and getting wrong answers. Things will go wrong, and you need to know why they went wrong. And so the idea that this sometimes seems a little tedious, why do I need to do it? You do. If you're going to be a good operator, you need to understand what your instrument's doing and how it's doing it. Because there will always be some catch someplace, and you need to be aware of it. So, anyway, let's just say pay attention. Anyway, that's the idea. No, always try to understand the instrument that you're using. Just good practice. So this is a little more detail on the split and splitless injection. So let's say we've got our gas cylinder over here, we've got our flow control, we have 54 mils per minute. And we'll say it's hydrogen coming into our system. Only 3 mils per minute of that, we've got it set up in this way, 3 mils per minute just go right straight across and out into the room. And you say, I wasted that? Why did I do that for? Well, this is 250 degrees centigrade. That's a rubber septum. and that rubber septum's going to degrade. It's going to be giving off volatile compounds. And so as this gives off volatile compounds because of its degradation, they can either go this way and screw up all your analytical work, or you can just flush them out here. So the volatiles from the rubber septum here will come down and they'll go that way. Because you're going to inject your sample down here. So you inject it outside of this flow that just keeps things clean. So you make your injection here, it goes poof, your sample goes poof. Here's your column here, maybe 1 mil per minute goes in here, then 50 mils per minute go this way. So we have a 1 to 50 split. Only 1/50th of my sample goes into my analytical system. 49/50ths go out the vent. So how is that determined by? 50 mils, so we got our poof here. Only 1 mil of that poof goes here, 50 mils of that poof go that direction. And again, we're just trying to get the sample size small enough that this little column isn't overloaded, so it still gives us good separation. We put too much sample on that column, it doesn't give you separation. So that's a split flow. This is our split less. Now I really want a lot more sample. I need it for sensitivity. It's going to hurt me for separating power, but I need to see material. So this is the same. Here comes 54 mils again, 3 mils across here, a microwave injection into here, poof. But what the way the system's set up is that it shuts off this vent. This exit closes, and this one opens up. So we have nothing coming out down here, and all of the, or almost all the flow goes across here. So I make my poof here, and very slowly it's going to move. It has no place to go. It can't get out of here. The only place that flow could go is down into the column. And so I can spend the better part of a minute simply dumping onto the column, onto the column, onto the column. Because there's no chance here. Then this is set, so it opens up. Then we flush this out, get rid of our samples. So instead of taking 1/50th now, we're going to be probably taking, maybe 1/10 of the sample. So we've increased our sensitivity substantially by permitting a bigger amount of sample to enter our column by closing off that vent for a bit. On column is when we really want we sample that we think may be thermally degradable. We don't want to put it in 200 degrees centigrade, it may degrade 250 centigrade. So what we do is we've got this type of an injection port. There's just a gas flow coming in, a little bit of split going out, and the rest going into our column. We got a syringe up here, and we got a really long needle of that syringe. And so we stick that syringe, we start poking in here, it goes to this rubber valve, it goes down, 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 down here, into the column. And so I'm making my injection down here in the column. This isn't a heated area. So my injection just goes down here. I put it down very slowly, and I can put my sample down here. And that can be 30 centigrade, 40 centigrade instead of 200, 250 degrees centigrade. So it's a nice way, if you've got heat-sensitive materials, to not do damage.
So is the injection port still at 230 degrees?
Not this one.
So you don't have injection, you don't have an injection.
It's almost ambient.
So you don't turn it on, basically turn it on.
Right. It's a different design completely. Yep. So that's kind of how we get our samples into the system. Now we've got to think about separation. Okay, we're going to need some kind of a column for a station to hold the stationary phase. And back in my days when I started chromatography, we had a stainless steel column or a glass column like this, typically about 1/4 inch in diameter, and that would be 6, 8, 10 feet long. And there'd be granular material in here, our stationary phase. The granular material could have different coatings. So I could use a certain coating that really loved certain analytes. I could change the material inside to something that likes a different analyte. So I could put different packings inside of this column to change my stationary phase. Well, that was a nice idea, but it really wasn't theoretically very sound. And so over time, we've progressed to use a capillary column. So this column replaces that capillary column, or this called the pack column, is a capillary column. So this is going to be 0.25 millimeters, quarter of a millimeter in diameter. And it's going to be 30 meters long, 15 to 100 meters actually. So I've got this tremendously long column of a very, very tiny diameter. There's no packing inside of it. It's completely open. It's an open tube. But I've hit a few micron film thickness of different materials inside of that column. So that column is coated on the inside with different types of materials. And so I can put a material in here that's very polar. I can coat the walls with a very polar material. Then polar compounds are going to like that stationary phase and be held up to different degrees. I can put a very non-polar coating in, so non-polar compounds react with this and get slowed down and get separated. That's kind of neat. Glass, it can actually tie that glass to the bowl. It's so strong, so thin that it can tie to the bowl. You'll get a chance to see them when you do the lab on that section. There are some types of columns like this that can actually have a fairly heavy coating, but they're not used very often. They're called porous layer open tubular columns. But they don't, not the workhorse. This is our workhorse, a capillary with this thin film of specialized coating on the inside. These are specialty types columns. Generally fused silicon, you bet, strong and inert. Inner diameters, what kind of size are we talking about? I said 0.25. That's normally what we use. But we find anywhere from 0.1 millimeters, that's tiny, to 0.53 millimeters in diameter. So they're still very, very small columns. The length, oftentimes, it can be from whatever you eject the sample, you got to get over the detector. It can be that short. Or it can be as much as 60 or 100 meters long. You have columns that range in diameter and range in length. What do you need for separation? And again, coatings, you can have many different coatings, you have many different coating thicknesses inside of your column. So a lot of opportunity here, a lot of variability you can choose from when you start designing the column. At one time, we had over 300 different coatings. We had the pack columns, the granular columns, had over 300 different things you could put in that packing. Today, there's only, what, 1, 2, 3, 4, 5, 6, 7, 8, 9 different coatings. So we've gone from 300 different choices to 9 different choices. Why? These small columns are so efficient. We don't need to have that packing, that stationary phase, do as much work. It's just a really efficient column, good separation. So instead of having 300, like I say, these 9 will do the separations that we want. They'll have the right interaction with our analytes. Question always comes up, what column should we use? So we have 14 different choices. Which one do we use? In general, first you go for the published literature. You go to the library, so to speak. I guess we don't do that anymore, do we? We go to Google instead. And so you look for this type of separation. Has anybody ever done this separation before? It's a big world and we have access to it. And very commonly, you will find, most likely you will find, somebody's done this separation before. And you look at you can get a copy of their paper then, and you simply say, are they doing the separation you want? And if they do, so what did they use as a column? So again, looking for what people have published before, the approaches that they've taken. You never quit with that because it's unwise to think that somebody has always the best answer. There might be a better way to do it. So you take that and say, okay, so-and-so did it this way. Is this the way? Is this the best way? Based on what you've learned in your experience. So you start off with a published, but you think about it. Is this the best choice? There are journal articles, there are compilations of this compound can be separated from this compound on this type of a column. And so we talk about retention indices. So there's also data tables. So this is published publications. This is simply a compilation of all this work that's been done. And you can start looking through these COVATS indices or retention indice compilations. Journal articles, internal work. If you're working in a company, somebody else may have done this sometime at their time. So again, you look through the archives of your company and say, have we done this separation? How did we do it? Intuition is certainly another choice. If you know your compounds tend to be hydrophobic, doing something really hydrophobic materials, you want to use a hydrophobic column. You want some interaction between that column and your compounds. If your compounds are polar, okay, then you want a polar column. So intuition says, yeah, I can get some guidelines in this. We can think about like structures. What's our stationary phase? What's that coding? What kind of molecules do we like to give a try? Sometimes we have no idea. We have absolutely no idea what we're separating, what we're looking for. I've had people walk into our laboratory down there with a piece of sheetrock from their house and says, my house stinks. And I think it's coming from the sheetrock. Can you help me? I don't know. What would you find in sheetrock? I think if I looked in the literature, I might not find much in the way of answers. And so there are times when you have no idea. It comes out of the clear blue. And you say, I have no idea. I'm going to start with a nonpolar column. Why? Because they're exceedingly durable. They cover a broad range of materials. They may not be the best, but they're the right place to start because they are so durable. I can heat these columns to 300, 400 degrees centigrade. You know, if there's something that really doesn't want to come out of that column, I can heat the heck out of that column. I'll get it. And I can't do that with my more polar materials. They degrade. My columns will degrade. So I start with a nonpolar column and give that a try first. But you always get the best amount of sample information you can get. Yep, you start with a nonpolar. If that doesn't work, doesn't give you separation, you change to a polar. But you always start off with nonpolar. Like I say, they're much more durable. These things cost about $650 each. And so you don't like to destroy them. You want to look after them as best you can. So you start with your nonpolar. These are, like I say, labile. So chromatographic processes. When we do gas chromatography, we really take advantage of several different types of chromatography, several different principles of chromatography. You may have gone through each of these.
We talked briefly, yeah, haven't dive yet into all.
So these are different principles of chromatography. I guess principles of separation. And one of them is adsorption. And so a compound may simply adsorb to the surface of some material. So it's a surface absorption. And so we use techniques like this in our field. We will actually have an isolation, we isolate flavors out of a food. And we have an inert needle, and it's coated with a very, very thin film material. I put that down into the food. Flavor compounds will be absorbed on the surface of that needle. We pull that needle out, put it in the gas chromatograph at 200 degrees, poof, they get volatilized off and away they go down their merry way. So in some types of gas chromatography, we use that for separation. Really surface interactions with our column coating. Molecular exclusion, then you'll be learning more about that. The idea that your stationary phase will be porous. There'll be pores through it. And those pores can be varied in size. So if you put a mixture of analytes into that column and there's a gas coming through it, if those pores are big enough, some molecules will enter the pores and they'll take kind of a pathway. I'll go through this molecule, I'll go through this other particle and go this way. And they get slowed down. Other analytes that are too big to fit in the pores, they go poof, they go right through. So you can actually separate molecules based on their size. And that's what we use for separation of helium, hydrogen, oxygen, nitrogen. They're all different sized gases. So if I've got the right material and the right pore sizes, I can push the larger gases right through and slow down the ones that I want to measure. So And an interesting thing is we could take advantage of more than one of these techniques in gas chromatography. Partition, that's when we have this coating on the inside of the wall, and our analytes are actually going to dissolve in that coating. They're going to partition. They're going to decide, I want to be in that gas moving through, or I want to be solidified, not solidified, but if I want to dissolve into this coating. So this is solubility. We're looking at separation of solubility. Will a material want to be soluble in that coating, inside the column, or will it want to stay in the gas phase? So we can take advantage of these. The thing we have really going for us is we also separate based on volatility, vapor pressure. And so we will always be combining vapor pressure, volatility, with one of these other techniques. So we can combine techniques, which gives us really good power. So you'll see that when you do your fatty acid analysis, you start off your gas chromatographic run at a fairly low temperature. And so only those things that are really volatile are going to go in the gas phase and move along. But then you start warming that column up. The column's in an oven. Oh, now the next thing is, oh, that's a little more volatile. Oh, it's higher. It's driving into the gas phase. I keep on heating it. It drives kind of one group of compounds, another group of compounds into that gas phase to be moving along. So you're separating on the basis of volatility, boiling point as well. So we take advantage of this plus some combination here. It's an exceedingly efficient means of separating materials. The column coatings, as I said, we can have different coatings inside. I showed you a table that range from polar to non-polar. They always have trade names of one kind or another. The polar ones tend to be called carbowax. The non-polar are silicone-based. This is an ester base. This is an ester coating. This is a silicone coating. Silicone, exceedingly durable. Non-polar, as I said, very, very durable phases. These are not. These will break down with water, with acids, and heat. So very sensitive, but very, very valuable. They separate polar compounds for us. So what do we have? We've got our carrier gases. We've got our ejection part. We put our sample in. We have our column where we get, hopefully, our separation. As I said, we can take advantage of volatility of the compounds we want to separate. And so we put these columns inside of an oven. So we got our columns inside of an oven. Start out at a low temperature setting and gradually raise the temperature of the column to move things along. So, and these ovens can be controlled from about -60 centigrade. You've got a good tank of liquid nitrogen sitting next to you, connected to the instrument, to about 400 degrees. So that oven can vary, that column can vary in temperature from -60 to 400 degrees. So really the ability to control volatility as a separation technique. So what do we have next? So we get our column. Well, we got to detect these things somehow. And so what we do is, of course, make our injection, and we watch the screen these days. A kind of crummy peak. I should replace that with a nice sharp peak. We don't like fat peaks, we like sharp peaks. Then we can put more of them in our analyte. And so this is kind of how it goes on. Here's peak one, and finally here's the next one that comes out, and so on. So what are we getting? We're really out to separate compound one from compound one, compound two. And then we have to have some way of detecting them, or we don't. We got nothing as an output. So we need a detector, needless to say. And there's really many different types of detectors. They vary in sensitivity and they vary in selectivity. We can make some detectors that only measure certain classes of compounds. And that's really important. It can mean that I don't have to clean up my sample so much. If I only measure what I want, if the rest of the junk isn't detected, I can save a lot of cleanup time, a lot of sample preparation. So the idea, we can find different sensitivity, different selectivity for detectors. And what we'll do is we'll just go through the most common types. There are many different versions. This is the first detector that was built in 1954. It's called a thermal conductivity detector. a TCD, thermal conductivity detector. It's non-destructive. So here's our column coming in. So the column, the effluent of the column, we feed it into the detector. It comes through the detector and goes out the vent. So like this. This is our mobile phase, our carrier gas. And this happens to be heated. There's this electrical conductor in here that's heated. And so as this carrier gas comes across this heated conductor, it cools that conductor. It changes, it cools this particular element. And as you change the temperature of a metal, it changes its electrical conductivity, the ability to carry electricity. So our ability to carry electricity, again, depends upon how much this is cooled. So, okay. So we've got kind of a background. We have no compounds eluting. We've got some standard cooling, some electrical flow through this. Then when actually an analyte comes through, now it isn't just our carrier gas. There's another material in here that's going to cool that electrical conductor differently. And so it changes the temperature, it changes electrical flow when we start putting analytes through here. So we've got a kind of equilibrium, a certain amount of electrical flow through the system every time that composition changes. Something comes off the column and goes through a detector. It changes the temperature of that. Changing the temperature of that changes their electrical signal. So it's a fairly simple detector. It's called a universal detector because everything cools differently. Everything has a different thermal capacity. So I can run water in here. I can run any compound. The only thing I can't detect is the carrier gas itself. That's my reference. That's my baseline. But if I'm using hydrogen, I can measure helium. I can measure oxygen. I can measure water. I can measure sterols. I can measure fatty acids. I can measure sugars. You name it. So it's a universal detector. That's very attractive, the specificity, if that's what you want. The problem is it isn't overly sensitive. We need at least 10 to my 7th grams of some analyte coming through that detector per second. And you might say 10 to my 7th grams. Oh, that's a 10th of a microgram. That seems like a that seems like a small amount of material. It isn't. That's a bucket. We carry those things around in pails, figuratively. How's that? That's what they call bucket chemistry. And so if this is really poor, we can do much better than this by other detectors. So it's universal, but it's not very sensitive. Linear dynamic range also, you may have some component in your sample that's tiny, then you have another component that's like this, and you'd like to know how much is present of each of these. Well, if it's a linear response, that's good, but if it's not linear, we have a hard time judging concentration. So the idea of linear range is only 10,000. And so that's on the low side, as you'll see. So not overly linear, not overly sensitive, but wow, detects everything. This is a flame ionization. This is the workhorse that I mentioned before. So here's your column coming out. We've got our carrier gas moving up through here. We've got our hydrogen and air coming in here so I can have my flame. Right above my flame, I have electrical potential. This is grounded, and this is 300 volts. And so as we burn things containing carbon especially, we form ions. I carry electricity right across the flame. And so that's what I'm measuring, electrical flow across that flame. This is good for most organics. Almost any organic does a nice job, shows up here. Now I'm down to 10 to the minus 12 grams per second. If I get that flowing through my detector, I'm going to get a peak product. I'm going to get something detected. So I've gone from 10 to the minus 7 grams, 10 to the minus 12. Okay, now we're getting respectable. For organics, that's really quite good. Linear range. I can have two compounds present in my sample that vary by million to 10 million fold in concentration, and I'll still get a linear response, linear difference for measurement. There are special versions of this, but this is what probably 90% of our chromatography is based on. Flame ionization. Good, does most of the things we want. Electron capture, we certainly can use that. In this case, here's our column coming in, our analytes are coming and going right past here. This is a radioactive source. I'm sorry, the radioactive source is on the inside here. And so our gas sample comes in here, flows across here, and will go out. And so this is collecting electrons. So basically, we're having a nickel-63 or a tritium radioactive gives up electrons as it just sits and decays. So I've got this always giving off electrons and this always collecting electrons. That's baseline. I get some compound coming in here. If it likes electrons, it absorbs electrons. And so what happens is your analytes come around this and your current decreases, your electrical current flow decreases because your compounds are absorbing electrons. So here we've always got a constant current until our analytes go past and they absorb electrons and we get less stable. So we count that. So the halogens, conjugate carbonyls, nitriles, a few others. No response with ordinary organics. So you have all kinds of organic compounds in there you don't see, or water. Now we don't get too much better than that, 10 to the minus 14th grams. And so what this has been good for is a lot of pesticides. Pesticides, herbicides, those kinds of things. So not quite as linear, but really good sensitivity and selectivity. So I'm not going to see a lot of the garbage, but I'll tend to focus then on the pesticide and herbicide. There's some other ones that are again a little more selective. Chemiluminescence and also flame photometric. So we have the same kind of thing. The column comes in, burns whatever's in the flame. So we've got a photomultiplier tube here that senses the color of the flame. What's the emission of light as things burn? You've probably done this sometime, or at least I hope you have, where you've atomic emission spectroscopy. Go to the Science Museum. You can actually select different ion solutions, run it through the flame, and watch the color. The color changes as you have different ions, different metals present, or different elements, let's say, present. So what you're doing is measuring the color given off as you burn your sample. And that filter here gets rid of everything except what you want. So I may be interested in sulfur. So the only light that passes through is from burning of sulfur. So I can monitor electrical flow here. There's many different detectors, Fourier transfer, infrared. You can go on down the line, very specialized one. The one that's really given, yes, chromatography, the boost, of course, is mass spectrometry. And we won't get very far with that. We have to quit at 2 o'clock, 1 o'clock, quit?
Oh, you have 1 minute.
1 minute, oh, tons of time. But no, I won't get started on that. But I want to really demonstrate the utility of mass spectrometry coupled with gas chromatography. Mass spectrometry is a marvelous detector, and I'll show you how we use that in the lab. So, oh, then you get off early today. A whole minute. Oh.
Good.